everyone, welcome to Science Friday.
Here's some for E as well. The one on the top here is one of the ways that you can define E.
What makes a field more likely to have an unbalanced gender distribution?
So this can be, like in the case of this paper, gyrification or brain folds.
A neuroscientist started to look at the brain
computers, like the math
more as an
lectures,
interconnected
I mean, it's
very
incredibly negative consequences.
Not what I
they're
described.
terrifying.
Here. It's been fun meeting, every week or so to start talking about this work. So you can see here, these are earthquakes going off around the world. This starts in 2001, right? And then it's just showing you the earthquakes as they happen over time. And what you see is that there are lots of little flashes, right? And then every once in a while you get a big one. And that's how earthquakes work. Lots of little ones, a few big ones. Okay? And you also notice that they're not happening randomly, right? They're organized. And you can see now that we're up to 2008, some pretty clear lines. These are, of course, the plate boundaries. Okay, not all earthquakes happen on plate boundaries, but most do. Okay? I'm going to rewind here to 2004. I'm going to let it run for a minute, and then I'm going to pause it right here. You can see a big orange circle up here. This is the 2004 Sumatra Andaman earthquake. So we're going to be spending some time here. So where are we? Sumatra is hidden by this big orange circle here. But this is India, this is Sri Lanka, okay, the Horn of Africa, and Australia. So those will come up in some other slides. This earthquake happened on a subduction zone. Subduction zones host the biggest earthquakes, okay? And they also have a double hazard because often these earthquakes cause tsunamis. Okay, so this little GIF is kind of showing what happens. Over long time periods, stress builds up until finally it overcomes the frictional strength of the interface and you get an earthquake. And then that earthquake pushes the water column up. I gotta play again. Yeah. Pushes the water column up and you get a tsunami wave. So water goes up, gravity brings it down, and that energy continues to travel through the ocean. Okay? This is the fault, what's lighting up in red. That's the part that moves during the earthquake. Earthquakes are complicated. So you guys saw this part, this stuff going down, and this stuff is kind of locked against it because of friction, okay? And so until that strength is overcome, those are stuck together. When the earthquake happens, it starts actually at a point, and then it goes both up the fault, but also north or south. So you've got the earth moving in one way, and you've actually got the earthquake, the front of the earthquake traveling sometimes in an opposite direction. And that's true at subduction zones. So I'm going to talk more about that and kind of quickly get you guys up to speed on what the geometry looks like. So I'll be showing it from different angles and it can get confusing. Okay? Again, this is the fault. Faults are complicated systems, but we simplify them by saying it's one surface. Okay? And it is three-dimensional. You can see the red side here, but it's extending under the water there. Okay? It's at the interface of the two plates in the case of big subduction zone earthquakes. Okay, so that 2004 event, I mentioned it happened near the island of Sumatra. Here's the northern end of Sumatra here. Okay? earthquake over here, okay? This green blob shows us in Matthew the length that slipped during this earthquake, okay? This is 14,000 kilometers, all right? Not 14,000 meters, but 14,000 kilometers of land moved during this earthquake. So that is the distance from Los Angeles up to Portland. Okay, a huge amount of land. The earthquake started down here. Remember, the land is going like this, both before and during the earthquake. But the rupture front, where the front of the earthquake is, goes from south to north. Okay? There was shaking from this earthquake for about 6, 7, 8 minutes. It's a really long time when the ground is moving under your feet. Okay, this caused a huge tsunami. Here, these little white dots over here, that is this big 14,000 kilometers of land that moved. The tsunami is shown here. These are time contours. So every time you see a line, that's an hour since the earthquake. Right? So the waves came out. A couple of hours later, they hit Sri Lanka, India, and then went over and hit the Horn of Africa. After that, this is 5 hours here. Okay? And also Australia. It was a huge event, a big disaster, lots of people affected. Okay? So I'm so happy to be here today to talk to you about some work that or some research that I was working on for a long time that's coming out soon. This is with colleagues Tomas Ulrich and Elise Gabriel. I'll talk about Elise a little bit more later. I mentioned an earthquake is two things. It is slip along a fault. Okay? So again, that's the interface here. This is the structural model for one of our simulations. Here's this plate over here, and I've stripped away the overlying plate because I want you to see that yellow surface. That's the fault. That's where we show in our models movement, okay, and that's where the seismic waves are generated from. So up here, I'm going to show this as a little video, but this gray surface is the same as this surface. So it's under the ground, okay? What this little video shows is the rupture front moving from south to north here. Okay, and this is a speed in meters per second. It's not so important. What I want you to see again is that the earthquake is not in the same place at the same time everywhere, right? It moves. So this is what we get out of models. Not shown are the big seismic waves being generated and leaving that surface and going to shake the land around. Okay? These models are done with a program called SciSolve. It's an open source software. It solves the seismic wave equations. Okay? And I'll come back to this, but it's special because it can handle, see how this surface kind of waves a little bit? It's not a plane, right? It's not flat. So we can handle that. These little gray things up here, those are splay faults. So those are more faults that are coming off this major surface here. And you can handle that. And you can also
Hi everyone, if you haven't gone to the Haunted House yet, please visit the WRC. 9th and 10th are in flex now, so if you haven't gone to the Haunted House, remember to go there before class starts at 12:30.
There will be time.
And there are cookies in the Rosenberg courtyard after you visit the Haunted House. Or before. Thank you.
All right. The other thing SciSolve does really well is it handles different things around this fault. So whether the rocks are mushy or really stiff, it can handle that. It can understand that behavior, it can model that behavior. We couple these models to tsunami models. These are run with Samoa. So very quickly you saw the earthquake ripping through and the start of the waves over here. Once again, this is Sumatra. This is India, this is Sri Lanka. Okay, and you can see the waves propagating outward from there. Okay? Red is up and blue is down. And I'll show more of that later. So these are on Samoa. Okay? So, how did I find myself studying this earthquake from 2004 okay, the part one is the life. All right? My interests have had tectonic shifts, okay? And I have lived on 3 different tectonic plates, all right? So hence this curvy, crazy path. As an example, I've listed here my different college majors during my undergraduate years. And there's some variety there. And I remember thinking seriously about all of these and like diving into them, and then changing my mind. All right, I ended up with a major in geological sciences, which I love. And as one does with a degree in geology, I went on to study international development for a while, okay? Then I found myself working at the American Red Cross. That was here in the Bay Area. And I worked there for a couple of years. And during that time, I went to a conference. And it was a conference between the American Red Cross, the U.S. Geological Survey, the California Emergency Management Office, and PG&E. And Dr. Mary Lou Zobak gave a talk at this conference. She worked at the U.S. Geological Survey, and I loved her talk. And I don't remember what it was about, but I loved it. And I went up and I talked to her afterwards. And for whatever reason, I shared my dreams with her. And I said, I'm working at the Red Cross, and I love the mission. The mission of the Red Cross is to shelter and feed people after disasters. It's very simple. I loved the volunteers I was working with. They were great. And I was bored to tears. Okay? And my day-to-day work was very administrative, a lot of people management, and I really missed science. So I told her all this. I said, I want to do something that's science, but it's also society. You know, I want to be doing that work, but I want to know that it's helping people. And she gave me advice that at that time really resonated with me. And I'm not offering this as advice to all of you. But certainly at that moment, what she told me was sort of the kick I needed in a direction I was already thinking of. And she said, go back to school, get your PhD in whatever you're curious about, and with that expertise, you will have many career options open to you, okay? So that resonated with me at the time. Once again, that's not a universal call to go sign up for a PhD program, okay? But that is what I did, and I loved it. It was really great. Several years after that, I found myself in Munich, and I had been hired by Elise Gabriel, who's about my age, to be a geologist on a project where they were modeling earthquakes with these big, three-dimensional, do-everything models that I mentioned earlier. Okay? This was a brief meeting that meant a lot to me. This was the beginning of a longer collegial relationship, and also a personal friendship. Elise is one of my dear friends, and we had a great group. There were engineers, there were physicists, there were computer scientists, there were numerical methods people, okay? I was the geologist, sort of. And these were some of my happiest years doing research. It was a really wonderful group. So I really agree that life is full of chance meetings, and it's also full of enduring relationships, okay? All right, so what about the science? So this is really a tale of 2 earthquakes, okay? I already mentioned the 2004 event. In 2011, you guys probably remember the Tohoku earthquake and tsunami, right? This was a huge event, and again, very devastating. Japan is one of the best instrumented places in the world. It is the best, and they have some of the best earthquake research and the best science in general going on. When this event happened, well, let me start here. The paradigm when the 2004 event happened, and this gets a little technical, but hang with me, was that this pink stuff would slip, but these yellow sediments here, too mushy, couldn't sustain earthquake slip. Tohoku was so well instrumented here that we scientists, I don't know, people who interpreted the data, saw earthquake slip happened all the way up to the trench. That's where this intersection comes to the surface. It didn't just slip a a little bit, it slipped 30 meters. Okay? This caused a huge paradigm shift. So instead of slipping restricted at depth, suddenly there was this possibility that it came all the way to the surface. And people said, aha, maybe that's why these events cause such big tsunamis. Okay? Before they thought, you must need these little faults that are more vertical so that the earth can go up and the water column can get pushed up, and therefore you get a tsunami. Okay? This kind of thing is huge in science. Before this, nobody looked at these sediments. They didn't really know what they were. Every model or interpretation that was done included no motion here. Okay? So this was a big paradigm shift, and what happened was people started to go back to other places and look at older earthquakes. So they actually went out and drilled these sediments here, okay, and they found actually that they were quite strong. What about technology? This is the third part of how I found myself working on this earthquake. Okay? I'm just going to say this quickly here, but in order to study these two sorts of scenarios, you need three things. You need to have a 3D system in your model. You need to be able to get these splay faults. This is weird. Meshing of low-angle intersections, what does that mean? Well, it turns out when you do numerical modeling, you need to solve your math problems at thousands of points in your three-dimensional model. And places where you've got things intersecting at low angles are really, really hard to solve math problems at. All right, so this was like sounds small, but it was huge. And actually, this is still like not a great, it's not like super well done, but it's good enough now. You also need to be able to model both stiff rocks and mushy rocks. Okay, and that is also key for this. And SciSol can do all of these things, and it's still the only software that can handle those things. Okay, and also model earthquake rupture dynamics, seismic wave propagation. Right. So the hypothesis was that slip to the sea floor is possible if your sediments are actually lithified and not really mushy, and that this is the situation at the Sumatra-Andaman Trench. Well, mushier, weaker sediments wouldn't allow this slip to go all the way to the surface. So remember, this had been the idea, but no one had been able to check it with a numerical model. Okay? And that splay faults are perhaps secondary to the tsunami generation. So what were the methods? Build an earthquake model that matches Sumatra, okay? Take that base model and modify it. So we've got three scenarios, one with strong sediments around the fault, one with weak sediments, and the base model. Then take those and use the output from those to model three tsunami scenarios, and evaluate that against data from the observations of the tsunami. Okay, I have three more slides. One is this. The three earthquake scenarios are indistinguishable by earthquake observations. These are different scenarios, the output is different, but when you compare them to the data, and there are numerous types that I'm not going into here, you can't tell which is better. If you build one, you'd say, hey, this is a pretty good model. If you build another, you'd say, hey, this one's pretty good too. Okay? So they're indistinguishable on that. And they get all the big stuff. They get the right earthquake magnitude. In this case, I'm showing GPS. These are vectors for any physics folks out there. So they're showing the magnitude and the direction of how the ground moved horizontally. Okay? And they're comparing data in blue at little instruments on these little islands to the model results in red. This is the vertical ground displacement. Okay? And then you can see also the displacement at the sea floor. Red is up and blue is down here. Okay? So all the models did pretty well against this. Yeah, Lou.
I'm just trying to understand. So what's the difference between on the image on the right, what's the difference between the red kind of like watercolory type stuff and the red arrows?
The red arrows are, well, the blue are the data at GPS stations showing vertical motion.
Right.
And the red is the model.
Right.
This is model results. We don't have data everywhere. Okay. So this is overlaid by the model result showing what happened at the sea floor in the vertical direction. So it went up maybe, I don't know, up to 4.5 meters here, more at the trench.
Right.
And it actually goes down when you're on the downside of the fault.
But the blue is also modeled.
Blue is also modeled.
Got it, okay.
Yep,
That was
yep,
okay.
yeah. All right, this is what goes into the tsunami model. It's actually 3 directions of motion, but this is showing the vertical component. Yeah.
So just a question for context that I've never seen on these before.
Yeah.
The overlay of red and blue arrows, for my context, is that a model that's pretty good or
Yeah.
not very good? Like what?
It's pretty good.
Okay.
It's pretty good. It's sparse data. Actually, when you remember this is 14,000 kilometers, it's sparse data. And the models are general. They don't incorporate a lot of the heterogeneities that are actually in the Earth. So yes, this is pretty good. Particularly down here. That's 12 minutes. There. But particularly down here, not so much right here, right? But it's okay. Yeah, Mark.
So if the models all reproduce similar growth features, why do they produce different tsunamis?
Great question. So they produce same growth features for when we compare against data that we have. What's really hard with earthquakes is that we don't have great data to compare stuff to. They vary a lot near the trench. This is where the fault comes to the sea floor. Okay? And so this is the base model, for example. They also vary, I'll get to this, over here, by what happens off the fault. On the fault, this is the base model. These darker colors get up to 30 meters of slip. This is on the fault. Okay? The one with stronger sediments gets more purple near the surface. This is where the fault comes to the surface. Okay, this is up here. And then the weaker sediment model, there is no slip at the top of the fault. That's what we expected. That was the initial paradigm. That when you had weaker sediments here, you wouldn't get slip near the surface. The problem was that the thought was that indicated, no tsunami or less tsunami. And then off the fault. So these are model results. If we look at the base scenario, this is strain. So this is cracking, damaged rocks being crushed here, okay? It's moderate. If you model this with stronger sediments, there's less of that. The energy stays in the earthquake on the fault, actually. Weaker sediments, you get even more damage. Those sediments they get all crushed up, okay? So they do differ, but we don't have data to compare these results to. This is why numerical modeling for this work is really important, because data is so sparse. Yeah?
Would you say that for the weaker sediments model, the fact that there's more damage, that being rocks and stuff, it's all in the middle of the ocean rocks. We don't care about those, but it should reduce the amount of force that could be transmitted into the tsunami. So is the weaker sediments a better scenario?
That's what we would expect, right? Let's look at the tsunami results. These are a little hard to see. I know. But this is a model result. Luckily, there are like 3 islands here with little buoys that showed tsunami waves. Luckily, the Jason satellite passed over this region during these waves, while these waves were passing. So we do have this one line where we can get measurements of the sea surface height. So that's what's here. This is a trough of a trough of 1 meter, an uplift of 1 meter of the sea surface here. And this is along this line. So this is no tsunami out here, right? Blue is data. It's really noisy, bouncing around. Green is the weak sediment model. Huge tsunami, anomalously big, okay? So that's not a good model, but it's an interesting conclusion that weaker sediments can produce a strong wave, very strong. Okay? The Halloween colors here, orange and black, are both the base and the stronger sediment models, and they do quite well against the data. Okay, so the conclusion was that the weak sediment scenario produces the largest wave, but the stronger sediment scenario best matches the tsunami data. And I turn it over to you guys and say, do you agree? Not necessarily right here, right now, because you can't even really see this that well, but these kind of questions are very open. There are a lot of things unanswered in this work, okay? And a lot of stuff I didn't Okay, it's cutting edge science, but you're also, hopefully, this is helping with mitigation and preparation to understand how the geometry and the geology of a region influence the potential hazard. So that's the real takeaway, and I'd love to talk about the details, but that's where I've left it for today. And I really do want to thank the students who have been helping me over the past couple of weeks, and it's been really fun. So thanks for the opportunity.